In this video, we're going to discuss physical properties, boiling point, vapor pressure, and solubility. This is a classic graph for boiling point, and the element or the compounds I just highlighted, water, hydrogen fluoride, ammonia, and methane, are a classic way of explaining how the strength of intermolecular forces increases or changes boiling point, in this case increasing from bottom to top. So water has the highest boiling point, and that's because it exhibits hydrogen bonding. So hydrogen bonding is the strongest intermolecular force, and water has the capacity to form per molecule 4 hydrogen bonds with neighboring molecules. Hydrogen fluoride has the second highest because it also exhibits hydrogen bonding, but those are weaker hydrogen bonds. Furthermore, ammonia exhibits hydrogen bonding, but those are the weakest hydrogen bonds of the three. Methane is nonpolar, so it only exhibits London dispersion forces, the weakest type of intermolecular force. So that's a pretty easy way to explain that trend. Now, if we look at the second trend, so this is within the same group bonding hydrogen, so methane up to tin 4 hydride. And so what we see there is an increasing boiling point due to an increase in the strength of London dispersion forces. And why do they increase? Well, this is due to the larger central atom as you move from methane up to tin 4 hydride. Carbon 6 electrons, tin many more electrons. I can't recall exactly how many, but more electrons, greater chance of polarizing the electron cloud, therefore increased dispersion forces. This table shows some organic molecules and the boiling point. One thing to notice is the molecular mass is roughly the same. So what that's inferring is that the number of electrons are going to be pretty close. So the differences due to London dispersion forces only would be quite minor. If we look at propane, it is a nonpolar molecule. All those bonds are nonpolar, so it exhibits only London dispersion forces. So boiling point of 231 Kelvin, well below 0 degrees Celsius, makes sense. The 3 with the green star, the 4 with the green star, are all polar molecules. Ether has that dipole-dipole force due to the carbon-oxygen-carbon bond and arrangement. Chlorine is a slightly polar, carbon-chlorine bond is slightly polar. So all these molecules exhibit dipole-dipole forces, and so they would be stronger, and the increase in boiling point as you go down that group is due predominantly to the increase or difference in strength of those dipole-dipole forces. But they're all polar, and therefore all exhibit that type of force. Now we're going to talk about solubility. So if we look at this first image, there are 3 test tubes. First test tube contains methanol, which has a hydroxyl group, which we know is a polar group, so methanol is polar. The second test tube is water, which has an OH bond, and so we know water is polar. And the final one is cyclohexane, which only contains carbon-hydrogen and carbon-carbon bonding, so we know it's nonpolar. Now, this first test tube now contains water and the methanol. So you can notice there's a single phase only, so it would appear that the methanol has dissolved in the water, and that is the case. We have 2 polar liquids, and like dissolves like. So the methanol is quite soluble in water, so it dissolved fully. Now this third test tube, we can see that the water and methanol phase is still there, but the cyclohexane has been added to the water slash methanol mixture. And you can, if you look carefully, you can see that phase boundary above the water methanol mixture. You can just see the top of the cyclohexane. So cyclohexane is clearly less dense and does not mix. There's the phase of cyclohexane, and it has not mixed at all. So a polar substance and a non-polar substance will not be soluble in one another. Now we're going to look at vapor pressure. So what is vapor pressure? Well, vapor pressure is a pressure that can be measured and does exist due to the vapor of a liquid that is located above that liquid phase. And so you can think about liquids will always be converted into the vapor phase, evaporation. That's very common. Just think about puddles of water. But that liquid will vaporize and in so doing produce a gas. So in an open container, as in beaker number 1, there is no lid to the container, so we will get evaporation of the liquid, but it will leave the container. Eventually, the liquid is converted to vapor, all the vapor, and the container is empty because the vapor has simply moved to fill its space, which is the atmosphere. These other two beakers, beaker 2 and beaker 3, have been sealed. So we have a top on them. Now if we look at beaker number 2, we can pour a liquid into a beaker and put a lid on, and we will get, relatively speaking, the beginnings of an accumulation of vapor particles. So they begin to evaporate. Because it's sealed, they cannot leave. Eventually, over time, there's an equilibrium between the rate of evaporation, that is the rate at which things go from liquid to vapor phase, and the rate of condensation, that is things going from the vapor phase back into the liquid phase. And so you just get a lot more gas particles above the liquid. And if you measure this pressure, this would be the vapor pressure. So the vapor pressure, as was mentioned, is the pressure of a gas above its liquid in a sealed container. Now, what affects the vapor pressure? Well, what causes something to move from the liquid to the vapor phase? Well, that is the strength by which the particles are being held together. So if the particles in the liquid phase have strong intermolecular forces, they would be more difficult to separate. On the other hand, if the liquid molecules have, relatively speaking, a low or weak intermolecular forces, then they're going to easily go into the vapor phase. This would produce a high vapor pressure. The liquid particles are converted to vapor, and the vapor is above the liquid, more particles, greater vapor pressure, and again, it's due to weak intermolecular forces. Ethers are a good example of this, commonly liquid phase, but quite easily converted to the gas phase. So a low vapor pressure, on the other hand, is going to be caused by liquid molecules with a strong intermolecular force of attraction, strong IMFs between the liquid molecules. This could also apply to solid state. If you think about solid, those forces of attraction between solid molecules must be quite strong. So strong intermolecular forces, meaning it is much more difficult for the liquid molecules to be separated,